In the series Advanced Mathematics, we are going to start lecture 6 of chapter Vector Calculus, and in this lecture we will talk about surface integrals. So first we are going to look at the definition of surface integral. So in this case we are saying that f vector be a vector point function, this is any f vector given to us, and s be any given surface. So suppose we are talking about this is the surface S. Then the surface integral of f vector over S is the component of the integral of this f vector along the direction of, suppose I am talking about this is the normal direction, this is n cap, we are saying this is the surface S. We know that this direction it is given by the gradient of the function, the surface, if it is given by f of x y z, that is equal to c, then the gradient of this will give us the direction of the normal vector. So we are saying the integral of this f vector in the direction of this n cap, or the component of this integral of f vector in the direction of n cap, it is called the surface integral of f vector over S. So we are writing if n cap is the outward drawn normal to the surface, then ds vector to be the vector with the magnitude ds and the direction n cap, then the surface integral of f, it is given by f vector dot n cap into ds, or we are writing this is equal to double integral f vector dot ds vector, where this ds vector, this is over the surface S, this ds vector means this is the component of the small component. Suppose I am talking about this is the surface we have, then ds vector means I am taking the small component of the surface over here, this is d, this may be dx dy if it is xy plane, and the normal vector we have drawn. So ds vector means this is the small component ds and the direction we are considering n cap, then this gives us the ds vector. Now next we have, if the equation of the surface is phi of xyz is equal to c, we are writing this surface that we have, if its equation is phi of xyz is equal to c, then the normal vector, the direction of the normal to this surface, it is given by gradient of phi over the length of this gradient, it is n cap, this is the direction in the normal to this surface. Now if we are talking about the projection of ds vector on xy plane, then it is equal to dx into dy, that is the component of x, and these are the components of x and y. We are saying this is the surface we have, this is the xy plane. If we are talking about the projection over here, this is some component of ds vector. If we are talking about the projection in the xy plane, it will have the component dx dy in this direction. So we are writing this is equal to mod of n cap dot k cap into ds. Why? We are writing this ds has three components over here. One is in the direction of I vector, j vector and k vector. Now if we want to find the component in the direction of xy plane, we are taking the dot product with k vector, we are getting this answer. So what we obtain from this is that the value of ds is equal to dx dy over mod of n cap dot k cap. This thing will hold if we have this n cap dot k cap is not equal to 0. Similarly, we have other two values. We are saying ds is equal to dy dz over n cap dot I cap if n cap dot I cap is not equal to 0. And third we have is ds is equal to dz into dx over n cap dot j cap if n cap dot j cap is not equal to 0. So this is the definition of surface integral that we have. Now next we have is the flux across a surface. So definition we have is, if f vector is any vector function, then the total outward flux of f vector across the surface, it is given by the closed integral, the surface integral we are saying, it is f vector dot ds vector. And in our next lectures, we will prove that this value is equal to triple integral over divergence of f vector into dv. This is by the region enclosed by this surface integral over E. This thing we will prove, and this is the divergence theorem. This we will prove in our next lectures. So over here we are saying that if the flux F vector across a closed surface in the region E vanishes, then divergence of V is equal to divergence of F vector is equal to 0 for points in E, and hence F vector is solenoidal vector point function in E. These things we will see in detail in our next lectures. So now next we have the definition of volume integral. So if we are talking about the point function phi and the closed volume, the region E, then the definition of triple integral we already know. The triple integration over E, it is phi x y z dv. This definition we have already studied in the lecture of triple integration. Now if suppose in place of this point function we have the function f vector, which is the vector function, then we are saying that the triple integral over E of f vector x y z dv, this is equal to I cap triple integral f1 x y z dv and sum of all these components. Sum of all these components, that will give us the triple integral of the f vector. Next we have is evaluate double integral a vector dot n cap into ds over the entire surface S vector of the region in the first octant bounded by the cylinder x square plus z square is equal to 9, x is equal to 0, y is equal to 0, z is equal to 0, y is equal to 8, where a vector, its value is given in this form. So if we plot this region, we are saying suppose this is the x axis, y axis and z axis. This is x axis, this is y axis, this is z axis. The cylinder that is given to us is x square plus y square is equal to 9. So we are saying that the cylinder will be of this form. The cylinder will be of this form, and it is in the first octant we are saying. So from this side it is bounded by the yz plane, from this side it is bounded by the xy plane, this is bounded by the yz plane, and from this side it is being bounded by the xz plane. Next it is being given that it is bounded by y is equal to 8. So y is equal to 8 means we are talking about this portion. This is having the equation y is equal to 8. So when we are saying xz plane, it means we are saying x is equal to 0, this is z is equal to 0, and this is y is equal to 0. So x is equal to 0, y is equal to 0, z is equal to 0 is there, y is equal to 8 is there, and the equation of this surface we have, its equation is x square plus z square is equal to 9. So we are saying we have, these are the first 4 regions, S1, S2, S3, S4. These are the 4 regions we are talking about, and this is the surface we are having in the first octant. It is x square plus z square is equal to 9. Now the function a vector, it is given by this equation, and we have to find the triple integral. So first of all, on the surface S1, surface S1 means we are saying it is xy plane, that is z is equal to 0. We are talking about the double integral over S1 a vector dot n cap into ds. Now what is n cap for this surface S1? Now we are talking about the xy plane. We are having the equation over here, it is z is equal to 0. Now for this plane, if we look at this plane, the normal that we have, it is minus of k cap. It is in the downward direction. So we are having, it is double integral over the surface S1, and the function we have, it is 6z I cap plus 2x plus y times j cap minus x times k cap dot product with minus of k cap. So we are saying this is equal to double integral. When we are taking the dot product with k cap, we are talking about the projection of this figure on the xy plane. Now we are talking about, we have, this is the xy plane, and the projection of this figure in the xy plane, it will look like this. And the limits, first of all we are taking the dot products, we are left with is x. Then in place of ds we have it is dy dx, the projection in the xy plane. Now the limits for y we are having, it is varying from 0 to 8, and x is varying from 0 to 3. So when we integrate this value, the answer we obtain, that is equal to 36. So this is the value of integral on the surface S1. Now if we want to integrate on the surface S2, I am again plotting this figure over here. Now we are naming these surfaces as, we have named these surfaces, when we are talking about this YZ plane, this surface from this back side we are having, we are writing it is S2, and the normal if you will draw to this surface, it will be in the direction of minus I cap. Then we are having this surface S3, this surface we are talking about, and if we plot the normal to this surface, that will be minus of j cap. Then we are having this surface, we are saying this surface it is S4, and the normal to this surface it is given by, if you plot the normal to this surface, it is given by j cap. And last we have the surface of this cylinder, whose equation is x square plus z square is equal to 9, and the normal to this surface it will be given by 2x I cap plus 2z j cap divided by square root of 2x square plus 2z square. So these are the normals that we have. Now if we integrate over the surface S2, we are having the function a vector is equal to 6z I cap plus 2x plus y j cap minus xk cap. Now when we are talking about the surface S2, the normal we have it is minus I cap. So the integral will become double integral over surface S2, and the value we have it is a vector dot n cap into ds. So the answer we obtain, it is double integral minus 6z. Now the projection we are taking, it is in the yz plane. Now if we take the projection in the yz plane, the limits for y and z we have, they are varying from 0 to 8 and 0 to 3, and on solving this, the answer we obtain, it is minus 216. Next is, we have these two surfaces S3 and S4. For S3 we have it is minus j cap, and for S4 it is j cap. The limits for both these surfaces, they are different. So if we write the integral for both these surfaces, for S3 we are writing, for surface S3, the integral will become double integral over S3 a cap dot minus of j cap into ds. ds over here we are taking, it is gx dz. Then it is plus double integral over S4 a cap dot j cap into dx dz. On this surface S4 we are saying the value of y we have, that is equal to 8. So if we take the dot product over here, j cap we are saying, so on A3 S3 we are writing the value we obtain, it is double integral 2x, the value of y over here, it is, for this surface S3 the value of y is 0. Then we have it is dx dz, and it is minus sign over here. This is the integral over S3, and on S3, this S3, look at this S3, it is basically the circle x square plus z square is equal to 9. Then we are having plus double integral a cap dot j cap, it is 2x plus y. Now the value of y we have, it is 8, so it is 2x plus 8 into dx dz. We have dx dz, and the limits again in this case, it is x square plus z square is equal to 9. Now if we add both these values, we obtain this integral, both sum of both these integral, it is double integral over x square plus z square is equal to 9. When we add this value, it is minus 2x, this will become 0, 8 will come out of this integral. We are left with this dx dz. Now what is this thing representing? What this thing is representing? We are saying this is basically with this we have the condition that x and z are greater than equal to 0. We are talking about the first octant only. It means we are talking about the area of this circle in the first octant. It is 1 by 4 of the area. So we are getting 8 into 1 by 4 pi r square. So answer we obtain it is 18 times pi. So we are saying the sum of both these values, it is 18 times pi. Now last we are left with is the surface S5 and the unit vector we have already seen over here. So if we take the dot product with A vector, answer we obtain, we are talking about the surface S5, we are saying phi is equal to the n unit vector we have obtained, it is equal to x I cap plus z k cap over 3. This thing we have already seen. Now if we calculate the value of A vector dot n cap, the answer we obtain it is 6xz minus xz by 3. So value we obtain it is 5xz by 3. Now again if we look at this figure over here, we are saying we are integrating over this curved surface. The vector A cap dot n cap, we are saying n cap is the direction of the normal to this surface. We have taken the projection in the direction of this normal. So we are integrating over this surface, and the equation of this surface it is given by x square. The equation of this surface we have it is x square plus z square, that is equal to 9. So if we substitute the values over here, we are substituting x, this circle, the equation of this circle, we can write it is x is equal to 3 cos theta and z is equal to 3 sin theta. So this integral will become, we are talking about this integral, this will become the surface we are talking about, this ds we are saying, this will be equal to 3 times d theta into dy. So we are writing that the value of integral over S5 A vector dot n cap into ds, this is equal to double integral, it is in place of x we are writing it is 5 into 3 cos theta, in place of z we are writing it is 3 sin theta. We are taking the projection in the y theta plane now, it is 3, the answer we obtain it is 3 dy d theta, and the limits we have it is 0 to 8 and 0 to pi by 2. Now why we are getting this kind of answer, or why we are using this approach, because otherwise the answer we will have it is double integral 5xz by 3 dx dy, we are talking about dx dy, and the limits we have that is varying from x square plus z square is equal to 9. Now over here we have dx dy, over here we have x and z, but z and y they are not independent, z and y they are not independent. So what we have done to solve this integral, we have made this substitution that x is equal to 3 cos theta, y is equal to 3 sin theta, and from this we have obtained the value of ds, it is equal to 3 theta d dy. So if we write the value of ds vector, that is equal to x I cap plus z k cap by 3, this is the direction, and then we are writing it is 3 times d theta dy. So this is the value of the ds vector over here. So in place of solving this integral, our integral comes in this form, and when you solve this integration, the answer you will obtain it is 8 into 45 by 2 and integration 0 to pi by 2 sine of 2 theta d theta, and on solving this the answer you will obtain that is equal to 180. So final answer we obtain in this case, it is sum of all these values. We have to integrate A vector dot ds vector over s. So we are writing the values we have, it is 36 over s1, s2, s3, s4 and s5. So the final answer we obtain it is 18 pi. So this is the total value of this integral. Now next question we have is, we have to evaluate the surface integral. The value of a vector is given and S is the surface of the triangle whose vertices are, these are the vertices of the triangle. So if we plot this on the graph, we are saying this is x-axis, y-axis and z-axis. The triangle that is given to us, it is in this form. These are the points 2, 0, 0, this is 0, 2, 0 and this is the point 0, 0 and 4. Now if we calculate the, find the normal vector to this triangle, the equation of this triangle, it is given by x by 2 plus y by 2 plus z by 4 is equal to 1, that is 2x plus 2y plus z is equal to 4. So the direction of the normal, it is given by 2i cap plus 2j cap plus k cap divided by square root of 4 plus 4 plus 1. So the answer we obtain for this, that is equal to 1 by 3 into 2 I cap plus 2 j cap plus k cap. Now we have the value of a vector and this is the value of n cap. So if we calculate the value of a vector dot n cap, the answer we obtained is 1 by 3. We have this value over plus 2z square. So we are saying it is 2x plus 2z square minus 2zx and minus xy. This is the value of a vector dot n cap. Now if we calculate the value of double integral a vector dot n cap into ds, and we are substituting this is equal to double integral a vector dot n cap, and in place of ds we are writing it is dx dz divided by the value we have, it is n cap dot j cap. So we are writing this is equal to a vector dot n cap. We are not having the value of y over here, so we are substituting the y from this equation. We obtain this is double integral 1 by 3 into 2x plus 2z square minus 2zx minus x into, in place of y we are writing it is 1 by 2 into 4 minus 2x minus z. Then we have dx dz and the value of n dot j, this is the value of n cap dot j cap. The answer we have, that is equal to 2 by 3. So we are writing this is equal to this over 2 by 3, this 3 gets cancelled over here, and when you open all these terms, the answer we are left with is when you open these terms, you are left with is 1 by 4 double integral over the projection on the xz plane, and the values we have over here, it is 2x square plus 4z square minus 3xz into dx dz, and the limits we are taking over here, it is the equation of this plane we have, it is 2x plus 2y. The equation we have, it is 2x plus 2y plus z is equal to 4. We are taking the projection on the xz plane, so this term is 0. So we are having the equation 2x plus z is equal to 4. So we are saying that the value of x, it is varying from 0 to 4 minus z by 2, and the value of z will vary from 0 to 4. This is from 0 to 4. So if you substitute these limits, the answer you will obtain, it is 1 by 4 integration 0 to 4. The values we have, it is 2 by 3 into 2 minus z by 2 cube plus 8z square minus 2z cube minus 3 by 2z into 2 minus z minus 2 square times dz. Now if you integrate these values, the final answer you will obtain, the calculation these are shown over here, this is this value that we have obtained, and now if you open all these brackets, you will obtain the equation in this form. You will obtain the equation in this form. You can try these calculations at your own. You will obtain the equation in this form, and by integrating this value, you will obtain the final answer as 10. This is the final answer you will obtain in this case. So we are saying the value of the double integral over this surface, it is equal to 10. Next we have to evaluate the value of f vector dot ds vector. F vector is given and s is the surface bounded by this plane in the first octant. Again it is similar kind of situation. We are saying the plane we have, it is in this form. This is the equation of the plane. So if we plot the normal n cap over here, the value of n cap that we have, that is given by 2i cap plus 2j cap plus k cap divided by 2 square plus 2 square plus 1 square root. So the answer we have, it is 1 by 3 2i cap plus 2j cap plus k cap. Now to evaluate this integral, we are calculating the value of f vector dot ds vector, that is equal to f vector dot n cap into, suppose we are taking again the projection in the dxy plane. We are having over here n cap dot k cap. So we are saying the answer we obtain, that is equal to the value we have, it is 1 by 3 there. This 1 by 3 is there. Then we have, it is 2xy minus 2x square plus x plus z. Then we have dx dy divided by n cap dot k cap. The answer we have, it is 1 by 3. So this 1 by 3 gets cancelled over here. So what we are left with is this value. Now we want to remove this z from here. To eliminate this z, we are using this equation. So our integral becomes double integral 2xy minus 2x square plus x. In place of z we are writing plus 6 minus 2x minus 2y times dx dy, and the limits now we have from this equation, we are saying the limits now we have, it is 2x plus 2y is equal to 6, that is x plus y is equal to 3. So the integral becomes, it is double integration 2xy minus 2x square minus x minus 2y plus 6, then it is into dy dx. The limits, they are varying from 0 to 3 minus x and then 0 to 3. Now if we integrate these values, first of all we are integrating with respect to y. The answers we obtain, it is these calculations, these are shown over here. You can try these calculations. We are saying the integral we are left with is in this form. When you integrate with respect to y, then on integrating with respect to x, we are having this term. On simplifying this, we are having this term. Then by integrating with respect to x, we obtain the final answer in this form. So we are saying that the value of integral f vector dot ds vector over this region S, it is equal to 27 by 4. So this is the value of this integral. Next is find the value of this integral. This is given over here, this is dx dy and the surface S, where S is the curved surface of the cylinder x square plus y square plus z square is equal to 9, bounded by the plane x is equal to 0 and x is equal to 2. So if we plot this, we are talking about, we have the plane over here, this is the cylinder in this form. It is bounded from below by the surface x is equal to 0. It is bounded from above by the surface x is equal to 2. And the equation of this surface we have, it is y square plus z square is equal to 9. So the normal, if we plot to this surface, the normal at any point on this surface, that will be given by 2yj cap plus 2zk cap divided by the square root of y square 4y square plus 4z square. So this value we obtain, it is yj cap plus zk cap divided by square root of y square plus z square. And on this surface the value of y square plus z square is equal to 9. So we are writing this is equal to yj cap plus zk cap divided by 3. Now if we calculate the value of f vector dot n cap, f vector we are writing it is 2x square y square and 4z square. So when we take the dot product with j, we are left with is minus 1 by 3. We are writing it is 1 by 3 common. We are left with this minus y cube plus 4xz cube. Now we are having the terms over here y, x and z, and we are having the circle over here. So we make the substitution. That is, we substitute y is equal to 3 cos theta, z is equal to 3 sin theta. So what we obtain from this is that the value of ds we have it is 3 times dx into d theta into dx. The value of x, it is varying from 0 to 2, and the value of theta, that will vary from 0 to 2 pi. We are talking about, we have written this circle in this, these are the parametric equation of this circle. So our integral becomes, now this value, it will become double integral f vector dot n cap into ds, that is equal to double integral minus 27 cos cube theta plus 108 x sin cube theta into d theta dx, and the limits for theta we have it is 0 to 2 pi, and the limit for x we have it is 0 to 2. Now if we integrate these values, we are talking about this integration, we are getting this integral is equal to minus 54 integration 0 to 2 pi cos cube theta d theta minus integration 0 to 2 108 x dx integration 0 to 2 pi sin cube theta d theta. Now we are using the result that cos cube of 2 pi minus theta, that is equal to cos cube theta, and sin cube of 2 pi minus theta is equal to minus sin cube theta. So using this result, we are having integration 0 to 2 pi cos cube theta, that is equal to 2 times 0 to pi cos cube theta, and integration 0 to 2 pi sin cube theta, that is equal to 0. So on substituting these values, we obtain that integral over s f vector dot n cap into ds is equal to this, and this value is equal to 0. So the value of this integral, the total value of this integral, it comes out to be equal to 0. Now next question we have is find the flux of this f vector is given through the circular region S obtained by cutting the sphere x square plus y square plus z square is equal to a square by the plane y is equal to x. So we are saying that we have something like this. Then we have a sphere over here. This is the sphere we are saying. This is x axis, y axis and z axis. We are saying we have a line over here, that is y is equal to x. This is in the xy plane. Then we are talking about some plane like this, the intersecting plane with this sphere, and we have to, this is the region, the circular region S obtained by, we are talking about the circle on this plane, that is obtained by intersecting with this sphere. So if we plot the normal to this surface, then that equation, the equation of this plane, it is x minus y is equal to 0. So if we find the normal to this surface, its equation is x cap minus j cap divided by square root of 2. This is the value of n cap. Now if we calculate the value of f vector dot n cap, the answer we obtain, that is equal to square root of 2. Now we have to evaluate the value of double integral f vector dot n cap into ds over the surface S, that is equal to double integral square root of 2 into ds over the surface S. It is equal to square root 2, and the area of this circle. Now to evaluate the area of this circle, we are saying, we are having, this is the plane, we are saying this is y minus x is equal to 0, and the center of the sphere, it lies on this, and the sphere is passing in this way. So what we obtain is that the radius of this circle, that is equal to a, the center will lie at the point 0, 0, 0. So the area of this circle will be given by pi a square. So the answer we obtained is equal to square root 2 pi a square. So this is the value of this double integral. Next is, if f vector is equal to this, we have to evaluate the value of f vector dot dv over the volume V, where V is the region bounded by the surfaces. These are the surfaces that we have. This is z is equal to x square. So this is basically a parabolic cylinder and it is bounded by these planes. Now if we plot these curves, we are saying we have taken the projection of these curves in the zx plane. We are having, this is the z axis, this is the x axis, this is the parabola that we have in the xz plane, and this is varying towards y plane from y is equal to 0 to y is equal to 4. This is moving outwards, this is varying outwards from z is y is equal to 0 to y is equal to 4. And then we are having the lines over here. This is the line we have, it is x is equal to 2, and this is the line z is equal to 2 that we have. We are talking about x is equal to 2 and z is equal to 2. So we are talking about this region. Now if we write the value of integral, we are writing it is triple integral over v f vector dot f vector into dv, that is equal to triple integral over v. It is 2z I cap minus x j cap plus y k cap into dx dy dz. Now the limits for y that we will have, they are fixed, that y is varying from 0 to 4 for whole of this region. Then we are saying that we have two portions over here. One is this portion and another portion we have, it is this portion. So we divide this integral in two parts plus the integral in second part. In this first portion, the value of y, it is varying fixed, it is varying from 0 to 4 in both these cases. In this first portion, we are saying the value of z that is varying, it is varying from x square to 2, and the value of x that is varying, it is varying from 0 to square root 2. This we are talking about this portion. Then in the second portion, we are saying the value of z that is varying, it is varying from 2 to, we are saying it is varying from 2 to x square. It's varying from 2 to x square. And the value of x that is varying, it is varying from root 2 to 2. I am again explaining these two portions. I am talking about this region, this first integral. We are saying we are having, these are the x's, this is the equation, this is the equation. Now we are seeing how z is varying. Z is varying in this direction. At this point, the value of z that we have, it is equal to x square. So it is varying from x square to at this point the value of x we have, it is equal to 2. Similarly, in the second case, we are saying the region we have, we are having the portions in this form. We are saying that z starts from this point. Now we have drawn this line. So z is varying from 2 to z is equal to x square. Z is varying from these 2 points. So we obtain the integral in this form. So if you substitute the values over here, the answer we are obtaining, it is, this is the first integral we are getting on using these limits, and this is the second integral we have obtained over here. Now on solving these integrals, these are these values we have solved over here, that we have simplified these integrals, and on solving these values and substituting the limits, you can look at these calculations over here. These are just the simple integrations that we have. The final answer we are getting, it is this. So we are writing that this is the value of triple integral f vector dv over the volume V. Now it is important to note over here that this answer that we have over here, it is a vector quantity. This answer we have over here, it is a vector quantity, it is not a scalar quantity.